Hello and welcome. My name is Michael Hansen. I am an astrophysicist from the University of Copenhagen and is currently employed as a high school teacher at the Roskilde High School here in Denmark. Alright, so some time ago I promised that I wanted to do some introductory videos or reference videos or whatever you want to call it about doing photometry in IRAF. And so there's been a lot of things on my plate lately, and yeah, I just haven't found the time for it, but now I do, and I want to sort of go over sort of the basics about stellar photometry in IRAF. So in the previous video, I sort of make sort of an appetizer for what photometry is, why we want it, and what it takes. So, like I said, at that time, you need. I've made my checklist here, and as you can see, I've moved it around a little bit. I used one of the reference manuals for photometry in IRAF, and that is why I have changed the this shortlist or checklist a little bit. So, but again, the prerequisites you need for photometry is some target observations. That is the stars that you actually want to know the photometry of. You need some reference star observations. So with that same telescope, with the same filters, and on the same night, you take observations of these reference or standard fields, they are also called. And then you need standard field photometry. So you need someone who has done photometry on that standard field before you and sort of laid the ground for how you can do that. And finally, of course, you need the calibration data, you need the bias, you need the dark, you need the flat. For professional telescopes, like for example the sensor you have at the Nordic Optical Telescope or Very Large Telescope or whatever you have it, you usually don't need the dark frame because these chips are super cooled using liquid nitrogen, so that there's effectively no dark current on these chips. But for usual consumer products, for example, if you have iTelescope, which I have used for this session, you definitely need the darks. For the reference star photometry or the standard fields, I have come to find that this library here by Stetson, you can pause the video and put this, look at this homepage, the address up here, but I will also put it in my checklist here, so that I know that I need to put it in the file, the description for this video. Now, I should probably also mention that these videos here will be probably in 2 or 3 sessions, perhaps something like that. I will record it as one session, but I will probably scale it up or down a notch, so that you don't get 2 hours of looking at me doing photometry, but you get in sort of nice nice shorts videos. Alright, so this guy here he's called Stetson. He has made these photometric standard fields, and whatever field you choose to use here, now you can look at the rectascension and declination here, and from that you can sort of superimpose or calculate which of these fields you can actually use, whether you are on the southern or the northern hemisphere. But no matter what you choose to use here, I have used IC 1613, as you'll see, and also NGC 6205, which is also called M13. It's a this is a globular cluster, a relatively old cluster, and as far as I know it, the IC cluster up here is an open cluster. I might make a video at another time explaining in more depth the astronomical or astrophysical differences between open clusters and globular clusters. But for now, just see it as clusters of stars. So for this field here, you can see we have stars in all the photometry. Now, the standard thing, if you want to do, for example, a color magnitude diagram like you usually use for a Hertzsprung-Russell diagram, you would typically use the BVR. You actually only need the BV because you're doing V versus BV, B minus V. So again, this is going to take a little more in-depth explanation, but in astronomy we tend to have sort of two definitions of colors. One definition is, well, the obvious definition of a color. You look at something and it has a given color. It's red, it's blue, it's something like that. We use that for stars as well. So if we take an image, a color image of a star, we can say, well, that star is red, that star is blue, and so on. But in astronomy and particularly photometry, you also have a different definition of a color, and that is one magnitude minus another magnitude. And one of the most used color definitions is B minus V. So the blue part minus the visual part, or B minus V, yeah. But you can also take V minus R and so on, so forth. But the thing I wanted to mention here was, there wasn't. You can see here we have 153 in U, 467 in B, 468 in V, 397 in R, and 366 in I. Now, because it is the first time I have taken photometry of that particular cluster here, that field here, using iTelescope, I tried to calculate, but I didn't get the photometry, the integration time, the exposure time set correctly. So effectively, my U fields are so poor that I haven't included them. But we have both for B, V, R, and I. Yeah. In any case, what you need to do what I do is you need the position, this one here. I have downloaded it, and you need the photometry, the actual photometry. Now, there's not time in this video to show you exactly how I have changed. Let's try to open it, because what Stetson gives you is photometry in this setup here. So you have the name of the star, you have U, the error in U, some ends, I think it's the number of stars, then or iterations or something like that. You have the B and the error in B and V and error and so on and so forth. But this is not exactly how IRAF is taking these parameters. So let's just take a quick peek at how IRAF does that. So let's take let's see, is IRAF, and then it's nowhere, 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 no hour, no ow, no ow, and then it is Digfot and Deofot. Is it? No, wait a second. It's Fotcal there. And catalogs. Alright, so here you have what you basically need. So you can use the Landalt, and I can show you these. Let's see what that is. In Landalt, it seems to be, I haven't looked at that before. It seems to be the positions, but in any case, let's see, Landalt. These are the. Alright, so let's take a look at F-Landalt. This is the format, so you have V, VV, UB, VR, RI, and VI. So this is a special, you have the V magnitude, and then you have the B minus V, the color, the U minus B, the V minus I, the R minus I, and the V minus I. So you need that in your catalog. I can show you what I have used there. So this is how I have defined it. So you have U error, B error, V error, R error, and I error. And this sort of basically tells IRAF where these are put in your catalog. So this is the column number. So let's take a look at the Stetson DAT. There it is. So this is how IRAF needs to take these parameters. So you have to have a field here with the ID, which is exactly 15 spaces long. This is what this tells you. This is U, it's 10 spaces long. Now you can change this if you want to. That's definitely okay. But I would retain this because I think it's neat. 10, 10, 10, 10, 10, 10. So you need to have that format. And as you can see, that it's definitely not what Stetson gives you. There's all kinds of things in here as well. So what I've done, and I hope that I can show you it. Let's see. No, it's not here. Let's see. I can't remember if I saved it out here on. I think it's it should be here. Let's take a look. So yeah. Let's see. Yes. This is the command that I use. So I have taken, for example, this is the catalog from M13 or NGC 62. No, sorry, that's IC 1613. Never mind, I've named it wrongfully. Alright, so you can see this is the catalog that I got from Stetson. And as far as I know, this should be the catalog that, yes. So you can see it puts an ID up here. That's not a problem because you only want to copy this part here and then put it into your catalog here. So that is what I've done. And basically, if you use this script here, and I can let you, it's basically awk or AVK or AWK that I've used. And what I tell it is that I want particular columns from my file. This is what I define here. And because I've made it as a bash script, as you can see here, I've made some input parameters. So I say this is the first parameter is file 1 and this is file 2. So basically, let's get a console. So what I want to do is I will say mkcat. Now I'm not in the correct folder, I'm just going to show you. So this is file in and this is file out. And if you use this precise setup here, and I would advise you to pause the video and then write this down, all of this you need. Then you can take any catalog from Stetson's page here. And you know what? I'm going to do something else just for you, viewers, because I am such a nice guy. I am going to put this on my list as well. Let's call it 11, things to put in a YouTube description. Yeah. So I'm going to write this as well, so you can put it in your and anything else almost, because I have a Python script and I'm not going to put that in the description as well. But you need that there. You need to stop the video and then put it in. All right. So this is what you need. This is the basic thing that you need. And for, I think for the catalog here, the minimum you need to have is an F file that defines, like this, how you declare your catalog, and that is the standard star catalog. This is the standard star catalog. As you can see, I have 3 things in here. These are for previous works, but you can basically tag any catalog that you have, any catalog that you find on Stetson's page, and then you can append it to a pre-existing catalog. And all you need to know then, and that takes a little bit of work, that is why you need the positional data, all you need to have is the names here. So you need to change your photometry find names to these names here, but I'm going to show you that in this video or in the next or whatever it's going to be. So you need the Stetson dat, which gives you the format, and then of course you need the Stetson dat, which is the catalog itself, and then you need something quite important. You need also the transformation equations. So these are sample transformation section for the new Stetson UVBR system that I've put in. So you have a filter color term. You need to look on the theory behind photometry to get more in-depth explanation. But these are terms that you need. So you have a filter color term, you have the 0-point magnitude offset, and then you have some extinction coefficient. So if you only have one standard star observation, I would highly recommend that you set it to constant. This is, and sorry for this being very unclear, but what you want to do then is to comment out this section here and then uncomment this section here. So what this section here says is that it's going to fit the filter term, the filter color term, the 0-point, and the extinction. And in order to fit the extinction, you basically need observations from the same night, from the same point in the sky, from the same position on the ground at different places on the sky, preferably through different parts of air mass, so that you get sort of an idea about what the extinction is. Now I have found these numbers from the BVR are from one of my courses at the university. The U and the I are something that I found in articles on the net. So what I'm going to do now, because I don't think that the photometry that I have from iTelescope is good enough to actually fit the extinction coefficient, I'm going to make it a constant. So I'm going to comment out all this, and then I'm going to uncomment all this. And down here you have the parameter, the transformation equations here. So this is basically what gives you the numbers you need to correct your photometry. But we're going to talk about that more, because we obviously don't need the U-fit. But if you want to do this, what I'm going to show you here, you need to know where your IRAF installation is on your computer. You need to find the NOAO, Digifod, FODCAL catalogs, and then you need to make a f.dat file. So I have called it Stetson, you can call it whatever you want. A format file that tells IRAF what the format of your catalog is. You need the catalog itself, and you need a file with the transformation equations. As far as I know, you don't need the in file, which what I think it is the position of these no, wait a second, it might actually be the catalog itself, as I think perhaps, yeah, I think it's the catalog itself. So you need 3 files in here. Alright, let's go back to where we came from. So that is data, astro, and OBBOO. So this is my basic catalog here. Let's minimize this one. This is my basic catalog. So I have the AppFont catalog, and I have some stuff in here. I'm not going to delete it, but I'm going to show you how you arrive at this. I'm also going to show you how I actually get the correct names for the stars, and so on and so forth. There is, as you will see when we get to it, the Calib catalog. This is the calibration files. You only need to, this is only relevant for some of the other video, the first video that I made, where I actually go through how you calibrate your data using IRAF. Then there's the reference stars. I've called it reference. We have M13 or NGC 6205 if you will, and IC 1613. And then we have the target catalog here. Now, the idea was that I wanted to try to find the magnitude of a variable star called OVBOO. So it's in this stellar formation, or Botus, the Hunter, I think it is. And it's an OV, so that's the type, but it should be a variable star. I wanted to get photometry of several points so I could get the magnitude difference over time, but unfortunately I don't think that I have had enough integration time in order to actually get the photometry, but we'll see that when because to be honest, DeoFind, which we're going to use to find stars, can actually find things that I usually cannot see. I have found that, so yeah. Alright, so let's close all the things down other than the checklist. I hope that I have set the stage for what you need in order to get started with what we're going to do at this point. Whether you want to do it stepwise with me, so that I tell you something that you have to do and then you pause the video and you do it yourself, and then so on and so forth, or whether you want to whether you want to just see the videos at one mass, all the videos in a row, and then try to do it yourself. That is completely up to you, obviously, because I can't feel when you pause the video. Well, to be honest, I really don't care. So you can do it as you wish. Yeah. Alright, so let's get started. So I am using IRAF, and that comes with the Eureka package, which unfortunately is obsolete now. You probably cannot download it from anywhere, but the main difference between IRAF and IRAF is that IRAF is, well, easier to use technically. It's the same program, it's the same things that you need to do, but IRAF is more clickable, if you will. You're going to see that. Let's start it up, if it so pleases. Oh, it did. Alright, so now we are in PyRAF or IRAF. If you have IRAF, your toolbox should look basically the same. You should go on the hunt for a task that is called star mark. I use it. You can use another task which I cannot remember the name of. It's also something called mark star. It's not star mark, but it is something mark. I can try. Let's see if it can find it. No, it's not that. But I cannot. Let's see if it can find. No, it cannot. But I can show you how it looks like this. I'm going to show you what it does. Also, we need to have DS9 installed and open. If you have again downloaded Eureka, the Eureka package, you will have a version of DS9 in your file, in your library. If you are going to download DS9 from the web, just remember that please call it SAO DS9 or SAO image DS9, something SAO image, something like that, because obviously if you just type in DS9 and search for that, you'll get a lot of hits for Star Trek DS9. Yeah, I have noticed that when I instructed my students at the high school in order to how to get DS9. But this is the basic layout that we need. I also like to have sort of a basic terminal open. So this is my PyRAF terminal, IRAF terminal. This is my null terminal. Alright, so let's get started. Let's look at what's the first point on the checklist. We need to correct the air mass and we need to correct the air mass. So we can use the observatory and set air mass. So I'm not going to run it, but I'm just going to show you what these two packages do. So let's go in and look at the IC. Yeah, so we're in here. Alright, so I've removed all the coordinate files in here because we're going to run them again, so that's not relevant right now. Sorry, did I? No, I went into the right folder. Yes. Alright, so let's look at the EPA observatory. So basically what you need to tell IRAF in order to get sort of the correct position of a telescope for it to set the air mass correctly. So you need to tell IRAF where have I actually gotten the images from. So you need you can do this by hand. So you can just skip this I have up here, delete this, not the images, you need that, but the OBS ID you don't need. Then you can say the observatory is Mayhill. I've called it iTelescope Observatory, Mayhill, New Mexico. It's minus 105.52 blah, 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 at longitude, and then 32.9 blah, 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 at latitude. Then it's 2,225 meters above sea level, and the time zone is -6, and you can tell it to override Mayhill if you want. So you just you put in the files that you need to do it to, and then you say execute. I'm not going to do that because I've already done it. Remember to set this to images because you want to do it at images. You can, I actually put in these numbers here manually. I can try see if I can find the file that I did it on. Let's make this a little bit smaller. So again, we're going to server, Eureka, IRAF, I think it's still NOAA, and then it is, yeah, I'm not sure I can remember that. Obsutil, perhaps, no, Library. No. KPNO. No. Can't remember where it is. But you can probably search for it. Obsolete? No. I simply can't remember where it is. But there is a file, a list file that you can use where you can put in the things that you need. I've done that, but as far as I'm concerned, I think you can say fill out these points here. You don't need the override, but you can put in observatory, name, longitude, blah blah blah, and then you can set it to set and execute. And you don't need to have these filled out here, and then you will get you get what you have put here in your file, so that you can get it again by just putting the ops ID here. But I've done that, so my computer or my IRAF now know where my observatory is, and then we set the air mass. I'm not going to do that again because, well, I have done it before. But what you need to know is that when you get a file, an image from an observatory, and that is probably whether you're doing it on an amateur setup like iTelescope, or you're doing it at a professional telescope, you will most likely get the air mass at the observation start. But sorry, in order to get the correct air mass when you're doing photometry, you need the mid-observational air mass. So you need to know what was the air mass at the middle of the observation, because that is probably the most correct one. Now, you can probably imagine that the air mass will not change that much if you're doing short images, short integration images, but nevertheless you need to do that. So you need to fill out a lot of information here. So you need to tell it what is the input keyword. So that is most likely the beginning. What you want as output is the effective air mass. So you need to, well, it's not the middle, but you need to know what is sort of the effect, what is the air mass over the entire observation. That's probably a more correct way to describe it. Then you need to tell it the right ascension keyword, the declination keyword, the epoch keyword, the local sidereal time keyword, the universal time keyword, the date keyword, that's date ops for my part, the X time, that's the exposure time. You need to tell it what the air mass keyword, and that is all keywords in your FITS header. So let's just take a look at it and say there are two commands you can use, so two tasks. That's headit or hedit, where you can edit. Sorry, not gedit. Where you can edit the header of your file. So you can, if you have one of the things that you can do, and I haven't put it in here. Actually, perhaps I should do that. Just put it as a B. Set corrected time exposure. Exposure time. But let's put it in a parenthesis, something like that. No, let's just make it that this is an SMB. If you, for example, know that your chip, your detector, has a manual shutter, where you know how much time this manual shutter uses for changing from open to closed, that will affect the exposure time that you have. So that could probably something like some milliseconds or something like that. I don't know the shutter time for this FLI detected that was on the telescope that I used, not had, but used. So I haven't put that keyword in. But you could put in a keyword for something like X time, and